Okay, so I would just like to make two more comments about, uh, well, a couple more comments about matrix inverses. First of all, inverses do not always exist. And when does this happen? Well, suppose that I start off with, an augmented matrix like this. And let's suppose that my row operations I get a 0 row to the left of the bar in the middle. Then there is no inverse. So let's just do a quick example of this. Let's say, let's say we're looking at the matrix 1, 2, 3, 2, 3, 4, and 3, 5, 7. And let's pretend that we were in the looking for its inverse. In fact, let's look for its inverse. Well, what's the first thing that I'm going to do here? Let me make my eraser bigger. What will the first thing that I do here be? I've got a 1 in the upper left corner, so I'm going to take minus 2 row 1 and add that to row 2. I'm going to take minus 3 row 1 and add that to row 3, because what that does for me then is I get 1, 2, 3 up top, 1, 0, 0. Here I get 0. 2 times negative 2 is negative 4, so I get negative 1. And negative 2 times 3 is negative 6, plus 4 gives me negative 2. And over here I'll have minus 2, 1, 0. And down here I get 0. 2 times negative 3 is negative 6, plus 5 is negative 1. And 3 times negative 3 is negative 9, which plus 7 is equal to negative 2. Down here I get negative 3, 0, 1. Okay, now I'm going to take negative of row 2 to get a 1 here, and I get 1, 2, 3, 1, 0, 0, 0, 1, 2, 2, negative 1, 0, and 0, negative 1, negative 2, negative 3, 0, 1. Okay, what do I do here? I want to get rid of the 2 above the 1 right here. So I'll take negative 2 row 2 and add that to row 1. And I want to turn this 1 into a 0, so I can just add 1 and negative 1 to get 0. So row 2 plus row 3. And this leaves me with the top gives me 1, negative 2 plus 2 gives me 0, negative 4 plus the 3 gives me negative 1, negative 4 plus 1 gives me negative 3, negative 2 times negative 1 is 2, plus 0 gives me 2, 0. Right here it stays as 0, 1, 2, 2, negative 1, 0. And down here I get 0, 1, and negative 1 is 0, 2, and negative 2 is 0, and then 2 and negative 3 is negative 1, negative 1 and 0 is negative 1, and that's 1. Okay, so we run into a problem. I can't get this right side to be the identity matrix. In fact, what this implies is there is no inverse to the matrix. What was our original matrix? 1, 2, 3, 4, excuse me. That was supposed to be 2, 3, 4, 3, 5, 7. It's just what it is. Too bad. Life does that to us sometimes. Okay. Now, there's a special formula for 2 by 2 matrices. And it goes like this. The inverse to the matrix A, B, C, D is equal to the following. First, I take the scalar 1 over AD minus BC, and I multiply that by D negative B negative C A. Let me just sort of verify that this works. A, B, C, D, let's multiply this by this guy on the right without worrying about the scalar in front. So if I multiply this by D minus B minus C A, what do I get? A times D minus B times C, so I have AD minus BC in the upper left. A times negative B plus B times A, that's 0. C times D plus D times negative C, that's 0. And C times negative B plus D times A, that's the same thing, AD minus BC. So if I divide this guy by 1 over AD minus BC, this will become the identity matrix. So this is a nice formula. So this is the fact, and this is more or less the proof of the fact. So for example, if I wanted to take the inverse of the matrix 2, 1, 1, 2, it would be 1 over 2 times 2 minus 1 times 1 times the matrix. I swap A and D, but A and D are 2 and 2, so I just get 2 and 2. I make B and C negative, so I get negative 1 and negative 1. And so this is 1/3 times 2, negative 1, negative 1, 2, or 2/3 minus 1/3 minus 1/3 and 2/3. I encourage you to check that this is correct. Let's do one more example. Let's say I'm looking at the matrix 2, I don't know, 3, let's put I don't know, I'm just trying to think of something. An 8 here and a 5. Okay. To find its inverse, I take 1 over 2 times 8 minus 3 times 5 times, I swap the diagonal, I get 8 and 2. And I negate the other guys, I get negative 3 and negative 5. And this is equal to 1 over 16 minus 15, 8, negative 3, negative 5, 2. And this is just 1 over 1, so that's just 1. I get 8, negative 3, negative 5, 2. Okay. Well, there we go. And you can go ahead and check that this works out. I encourage you to check that. So let's note, though, if AD minus BC is equal to 0, this doesn't work. Okay. So for example, if I had something like 2, let's say 2, I'm going to make it work, 6, and 4 and 3, something like this. If I tried to take its inverse, I would get 1 over 2 times 6 minus 4 times 3 times negative 6, negative 2, negative 2, negative 6. Swap those guys. I forget the formula myself. 6, 2, negative 4, negative 3. And this gives me 1 over 12 minus 12, that's 1 over 0 times this matrix. So that actually leads to a problem. Okay, so this actually, it turns out that if AD minus BC is equal to 0, then the matrix actually has no inverse. So then, what we call this quantity AD minus BC for a 2 by 2 matrix ABCD, we call this the determinant. And just the basic fact is that if the determinant is non-zero, then the matrix has an inverse. Whereas if the determinant is equal to 0, then it has no inverse. And there is some vocabulary which says that if it has an inverse, we call it non-singular. Whereas if it has no inverse, we call it singular. Okay. That's I guess pretty much it. I'm trying to think if there's anything else that I wanted to say here. Yeah, I'll put up some applications or something like that soon, but for the time being, that's all that I really wanted to care about talking about.